Hi there. Welcome. This is Dr. Hisham Saeed. In this lesson, we'll learn about resource management and two important functions within this field, which is resource loading and resource allocation. So we will learn, these are the learning objectives here, so we'll know what's the purpose of resource management, what do we mean by resource loading and how we do it, explain and understand the impact of resource constraints and on scheduling construction projects, and learn about a new method to schedule such projects. So we call it resource constrained scheduling. So a resource, when I mean here a resource, is anything, any item that's needed to complete the construction activity. So anything, imagine any item physically, or even sometimes, spatial, and money. So like material, human, equipment, money, space, even is a resource that you need to execute the activities on the construction site. So project resource management is the process of first knowing what's needed for every activity, and then trying to satisfy these needs in a timely and also financial manner. So the resource management implies different tasks or different functions, covering here three main ones: resource loading, allocation, and leveling. In this course, we'll focus on resource allocation and resource loading and allocation. Resource leveling is more like an advanced technique to improve your schedule once it satisfies the resource constraints. So it's called also resource smoothing. So due to time limitations, we'll not cover it in this class or this lesson. So resource loading is basically finding the demand of a resource in every time period of the project. It's a week or a day, to be able to accomplish the scheduled activities. So the loading periods here, it's up to you. You can decide to make this resource loading diagram on a daily basis, weekly or monthly. So you get in the activity start and finish times, so it's basically the schedule, and you get the resource need of each activity per day. So if an activity needs to be done, to do an activity, you need a crew of 2 laborers, 2 workers. This is the number, 2 workers per day. So let's say an example here. So you have activities A through F. This is a mini project here. We're given the durations, we're giving the logic, and we're giving the resource need per day. So before we do the loading the resources on the activities, we need to first draw the activities as a bar chart. So this is exactly what we're doing here. A is a starting activity, and then B, C are following A, and then D depends on C, and then E depends on both D and F. So both of these. F depends on B. So by looking here, I can track here the longest path, which is A, C, D, and E. These lines here refer to the total float. So now when I load the resource, meaning that I look at these numbers here, A needs 2 resources per day. So this will be 2, 2, 2. Every day of A, I need 2 workers. And I'll do the same for the other activities. Then I will add up for every day the resource demand. So for days that have multiple activities happening, I know now what's the total demand for this resource. So for example, on the 7th day, there is a need for 7 laborers to perform the work, which is including activity D and activity F. And then using this total resource demand per day, I can draw this histogram. That histogram is following the activities when they are executed at their early times. But I can also show this histogram if the activities are drawn following their late times. So kind of pushing the non-critical activities all the way to the end of their kind of slack or float. So instead of having the B, for example, start at the beginning of day 4, now it starts at the beginning of day 6. You can see now that my resource demand will be something between these two. Like it will be a shape that this is the earliest here, or I can push some activities so I can skew that histogram to the end or more later in the timeline of the project. One question I will leave you to answer here: what's the relationship between these two histograms? Geometrically. So think about what's the thing that ties or relates these two histograms here. The resource demand or histogram on the early times and the other one following the late times. What is the relationship here? So that's the resource loading. It's just visually seeing what's the resource demand every day in the project, or every month, or every week. Next function within resource management is resource allocation. So, and what we learned when we did the critical path method is that it doesn't have any mention of resource demand and resource needs and resource constraints. So there are a lot of constraints are applied on the resources we need in construction. So for example, labor, you can't get all the labor and workers you need because there are limits. The availability of workers in an area, especially if you are a union signatory contractor, the union have a capacity to secure and provide the workers that you need and the trade people you need. An example, equipment. So there is limited number, especially tower cranes. If your project needs or is a high rise or requires a tower crane to move materials within the site, you will be surprised how many tower cranes are available nationwide. So it's not something that like a clip of your fingers, snap of your finger, you will have a tower crane. Material. So you have limited quantity of the materials you can secure because everyone wants this material also. So a good example is ready-mix concrete. If you go to a batch plant, they have a capacity they can provide per day, and it's not, your project is not the only one in the area, so you're competing on that quantity. So resource allocation here, what we mean is you do the scheduling calculations and you develop the schedule for projects that while recognizing their resource constraints. So resource allocation, another name for it is resource constrained scheduling. So let's say that revisiting this project that I did, resource loading, and developed that histogram of resources, let's say that I have now identified that I cannot secure more than 5 laborers per day. So I have drawn here my limit, which means that this is an over allocation. I have over allocations in the 7th, 8th, and 9th days, which means I cannot secure the laborers in these days, which means that this schedule is infeasible. So, by the way, just something I didn't mention is that this histogram is developed for every major resource you have. So for every major resource you have, so it's not only the laborers, I can develop a resource histogram for carpenters. For the major resources you have, carpenters are usually the main resource here in the US, Northern America. Or other things like what else? Like the ready-mix as a concrete, especially if your facility is really heavy on concrete structures. So for every major resource, you can develop a resource histogram. So for resource allocation now, this schedule, it's not the end of the game. You can actually change the execution time of the activities, so you don't have to do them on their early times. You push them later, but the problem here is you might end up with a longer duration of the project because your goal is to satisfy this constraint. So you're willing to sacrifice the shorter duration of the project that you would have had without considering the resource constraints. So it is expected to have an extension in the project duration to respect the constraint you have on the resources. So the objective here of resource allocation is to resolve resource conflicts, what we call over allocation, while minimizing extension to project duration. So for someone like you who did research applying decision-making support systems in construction, this is a very good optimization problem, so like satisfying a constraint while minimizing an objective function here, which is the duration of the project. So you can model it as an optimization problem and use optimization techniques. So linear programming or evolutionary algorithms like genetic algorithms. So it's a whole field. Don't be intimidated by these names or terms. But it is the use of computer and algorithms to solve this problem for us. It guarantees optimal plans, meaning that you guarantee that you will end up with the best schedule. In GA and evolutionary algorithms is not the case, but it's up to a high degree. You end up with the optimal, close to the optimal. On the other hand, if you don't have access to computers and your problem is not that huge to justify doing it on a computer, you can use heuristics. And you will also be surprised that commercial software like Microsoft Project, Primavera, P6 are using heuristics to perform the resource allocation functions within them. So heuristics here is just using the rule of thumbs, like which activity is more important? This one that has total float high or low? Like there are rules that you can use to tie break and select activities to execute and schedule before others. But because it's very rule of thumb kind of, it makes sense, yeah, pick this activity, there is no guarantee that you will end up with the optimal plan. On the other hand, optimization, because it's computer, it requires computer-based or algorithm-based, it requires time to develop it and implement it and run the algorithm, so especially if you're dealing with big projects. But on the heuristic side, it's not. It's just a very simple algorithm to apply it in a computer, or even use it as a paper-based, which we'll use in this course here. So there are different ways in the heuristics approach. There's the serious method and the parallel method. So in this course, we will learn about the serious method. So meaning serious here means that you're not considering multiple activities at the same time. You schedule an activity time one after the other, this is the procedure here to go over a little in detail and then apply it in an example. So the first thing, you need to perform a regular CPM calculations to identify the early and late times and the floats of each activity. And then we will have a specific table format to use, but you have this table, it's a bar chart table, but it has other columns to help us track which activity to schedule next. And then you set the timer. So we have the timer that we move through the timeline. So we set the timer t is equal to 1, or t is equal to 1 here is the first day, but really you set it in your time scale at 0. So at the beginning of day 1, basically you set the time as the beginning of day 1. And then at this time you examine what activities I can start, and you indicate that with this slash mark here. And then at this time, you select from all these activities you identified as possible to schedule, pick from them based on the following criteria. First, when you pick, the resource needs will not increase the resource demand in that day more than the constraint. So you're still respecting that resource constraint limit. And if you have multiple activities to pick from, then there are priority rules. The rule of thumbs, the heuristic. These are the rules here. You pick the ones that come with earliest late start from the CPM calculations you did. You pick the ones you would pick the ones that has the least total float. And then if you really now have two activities that have the same exact late start and total float, then you pick the one with the largest number of resources. If even that has a tie then pick randomly anyone. Again, randomly, then it's heuristic. You don't know what's the impact of that on scheduling the other future activities. So once you do that, you set the time. Now you move the timer, right? You move the timer to the next time point, which is the minimum of the finish times of the activities you scheduled before. And you repeat that process. It's a repetitive process, so every time you move the clock, you examine activities, which ones I should schedule, you have tiebreakers, and you keep moving through the time of the project until you schedule all the activities. So this is an example here. We will perform resource allocation for this project. And it's if you look at the logic here, E dependent on B, C, and D. So just to look at the CPM, it's already done, but in a typical problem, you will do it yourself. And then you look here at the critical path, A, D, E, and you look at the non-critical activities and identify also their total float. So I'm showing here the early times and the late times resource histograms. So that was the one of the kind of it's a good practice to know what's the status of this project. And you can see that our resource limit here is 3 labors. So in either the early times or the late times, we have issue with respecting this resource limit. These the values of 4 labors per day here are, of course, more than 3. So we need to perform resource allocation to resolve this conflict. And we expect, after we do the resource allocation, that the project duration will be more than 9 days. So we'll use this table here, and you can see it's kind of similar to bar chart, but you add more these tables here, or these columns, to be able to perform the resource allocation process. So this is the same exercise. I moved it to my whiteboard, virtual, and the first thing we will do here is we will write the total float and late start of the activities we have. So kind of I will repeat what the bar chart that I showed before, but now just as an activity on node kind of CPM. So just that's the same bar chart that I shown, but now as an activity on node. And you'll need to do here CPM calculations to find the early times and the late times, and also the critical path and floats for non-critical activities. Once you do that, you copy some values from this CPM, assuming no resource constraints, to the table we have. So I copied here the total float and late start, because remember, the tiebreakers we're dealing with are related to these 2 values. And then I will say I will set my timer for the first day, which is at the beginning of the first day is typically time 0. So if you look at activity A and the activity on node diagram, it starts at time 0, which is the beginning of day 1. So now if I look at the beginning of the project, the only activities I can schedule are the starting activities that have no preceding activities. So this is activity A. So this is why I kind of hash, with this mark here. Once now I identify the activities that I can schedule, I need to decide which activities to schedule. So here I have only one option, A. So just deciding to schedule A, and A here is 1 day, and it requires 2 resources per day. So that's it. Once I do that, I move the clock. So the next time that I move to is the end of A. And then once A is done, so I mark it on the activity on node, I now see that I can schedule B, C, and D. So these are the 3 options to schedule next. Which one now to schedule? We'll use the tie-breaking rules. So we will pick based on the earliest late start, the least total float, and the largest resource per day. So if I look here, the earliest late start D qualifies. So D here, once I schedule it, I make it now instead of a slash, I make it cross. So D is scheduled, so, and it's 5 days, and it needs 1 resource per day. I'm still below my limit, which is 3. So I'll be able to schedule more, right? Another activity. The second activity that respects the tie breaking here rules is activity C, because it has the least late start compared to B. So I will schedule C for 3 days, and every day is 1 resource. And I can see now, if I want to schedule B next at the same day, which is the beginning of day 2, its resource demand is 2, so if I do 2 at second day, so 2 plus 1 plus 1, that will make it 4 more than 3. So now I will stop scheduling at this time clock, and I will say that's it. And I will move my time clock to the next stop point, which is the minimum of the finish times of the activities that I just scheduled now. So now I see I move to the clock to, so once an activity finished, you move the time clock to there. So the time tick here is at the beginning of day 5. C is done, so I kind of mark it on the activity on node. And now once C is done, the preceding activities that I have here depends on C, yes, but also depends on B. So B didn't finish yet, or was not scheduled yet, and D didn't finish yet. So I cannot, like, let's say, E and F are candidate activities, not yet. Their predecessors are not finished yet. So I have only one option, which is B, so I schedule B 2 days and 2 resources per day, and I am now within my limit still, so that's good. And then move to the clock to the next point, which is now once an activity is done or finished, that's a possibility of scheduling another activity. So that's the beginning of day 7, and I have 2 activities done, B and D. So now I have B, C, and D marked now on the activity node. You can see now that E and F can be candidates to schedule one or all of them or both of them. Which one I should schedule? I look here, late start, they have the same value. First tiebreaker didn't work. Then I pick the next, which is the least total float. So then E wins. So E is the one that I will schedule here, and it's 3 resources per day for 3 days. That will consume all my resource constraint. And then after E is done, then I can schedule F, 1 resource per day for 3 days. And that's it. I'm done with all the activities in the schedule, in the project. I scheduled all of them, and you can see now that the project finished in 12 days. And it was originally scheduled, if I imagine no resource constraint, in 9 days. So I extended the project by 3 days to be able to actually execute it, because the resource limit here will prohibit me from executing that project. So that's simple. It's just a very serious, again, it's called serious method, because you move from the beginning to the end of the project. You handle one activity at a time. You pick the activities based on heuristic rules here, tiebreakers that we analyze. And in class, this is your task now, your kind of thing to work on. So check this example and try to work on it. We will work on it in class. So it's kind of a similar one. You have activities, you have the resource limit here is 4 carpenters. So first of all, draw the bar chart, load it with the resources, find, are you respecting this limit or not? Of course not, right? I will not give you a problem that's not a problem. But you will have here a constraint that need to be satisfied. So you will need to also to do resource allocation. All right. Good. So thanks for watching. Appreciate it. I will see you in other videos. Take care of yourself and those around you.